Good afternoon, everybody, and welcome to another Alliance for PE Pipe Roadshow-like program. I'm Drew Mueller with the Alliance for PE Pipe, and today we will be going through our good old HDPE 301 presentation. We call this the engineer's perspective. We're going to go in depth on some design considerations for those of you getting ready to install HDPE in your municipal systems. We have two excellent presenters for you today. We'll introduce them in just a moment, but first we want to cover a few basic housekeeping things. As always, we want to thank all our Alliance for PE Pipe members. These companies fund our organization. They make programs like this possible. If you want to buy the best pipe, the best fittings, the best equipment for your HDPE projects, you want to buy from these companies up on the screen. But a special thanks to IPP, Improved Piping Products. Darren Zeppelin and IPP are sponsoring the show today. Darren, do you want to come on the call and just take a couple moments to talk about IPP, the services and products you provide? There he
Sure
is.
do, Drew. Thank you very much. On behalf of Improved Piping Products, I'd like to thank the PE Alliance for hosting this event, but most importantly to the participants. We know that you have busy schedules, you're working hard, and it means a lot to us to take the time out to listen to Richard and Alan tell you about the positive impacts of polyethylene in our infrastructure today. So thank you. As Drew mentioned, my name is Zeppelin. I'm a territory manager for Improved Piping Products. Been with the company for a little over a year now. Previously have about 10 years experience in the polyethylene world, both at the manufacturing level and also a distribution level. Improved Piping Products is a 40-year-old family-owned company. We are based in San Antonio, Texas, where we produce polyethylene everywhere from 2-inch all the way to 63-inch. Most notably in the waterworks world, we produce anywhere from 18-inch all the way up to 54-inch J adapters, which you'll see some pictures of those. You'll see some in dips as well as IPS, and we do reducers in wall anchors, all 18-inch all the way up to 63-inch. With that, certainly want to get back to the presentation here and look forward to what you have to bring. So back to you, Drew and Peter. Take it away.
Hey, Darren, thanks a lot. I always appreciate you having you with us. If you want to join the Alliance, you can do so on our website, pepipe.org. If you are an engineer or a contractor, there is no fee to join. We have a great social media presence, over 15,000 followers on these three platforms, plus Instagram. We see our most activity on LinkedIn, but follow us on the platform of your choice. We are posting every single day. That website, pepipe.org, also has a great case study database, searchable by project type, by geographical location. So if you're considering a poly project in your municipality, chances are you can find someone close by who has done something similar in the past. We have two more webinars coming up on the schedule in March. The first one on March 10th is above ground. You know, this is a topic we get questions about all the time: above ground installation. How do I restrain the pipe, bridge crossings, things like that. We're going to go in depth on that topic. Richard and Alan, who are presenting today, will be the presenters on the 10th as well. And then a week later, March 17th, we'll be live from Tulsa, Oklahoma at McElroy Manufacturing's headquarters. McElroy makes the green machines used for butt fusion. We're going to demo several different machines, from the small manual fusion machines to a rolling hydraulic machine, all the way up to their new track machines that have a fully automatic function. So very excited about that. A couple resources we have for you. The engineers package. We haven't updated it yet for 2021, but we will be doing so soon. Still a great resource for anyone designing with HDPE. I have a lot of design guidelines. We have the Alliance's standard details and model specifications. Those details and specs you can copy and paste right into your spec when you're ready to start designing poly projects. We also include Plastic Pipe Institute's Handbook of Polyethylene Pipe. You know, they'll sell you a hardbound copy for $40. We'll give you the PDF for free. That's a phenomenal resource, really essential for anyone designing with polyethylene. I reference it every single day. We also want to plug the Poly podcast. This is something we've been working on for about 6-7 months now. Twice a month, we're releasing podcasts where we go in depth for about an hour with engineers from across the polyethylene industry. You can find that anywhere that you download your podcasts presently. And now we want to bring Alan Ambler and Richard Colassa onto the call. Alan's been working with the Alliance extensively over the last several years. He is an expert in all things trenchless installation. He literally wrote the book on pipe bursting. Alan, how are you today?
Doing very well, Drew. Thank you very much. I appreciate it.
Well, very happy to have you. And then Richard Colassa with WO Plastics, chemical engineer. He's taught me pretty much everything I know about how HDPE is made and used. And we also have Peter Dyke joining us from Charlottesville, Virginia. Peter, how are you today?
Greetings. Thanks for having me, Drew. And special shout out to our friend Richard Colassa, because Richard's special day is today. Comes once a year. Happy birthday, Richard.
Thank you very much, Peter. Don't feel a day older at all.
Now, you don't look any older either, Richard. All right, Drew, great job. Great job as usual. So here's how you can contact all of us. And Darren, tell us what your email address is. I didn't get that on there. I apologize. How can people contact IPP if they're so inclined? All right. Looks like we lost Darren.
I'll tell you, it's darren.zeppelin@ipp-inc.com. I'll get that on a slide for the end of the presentation, but please reach out to me if you have questions we don't get to today. If you need credit for attending today, or if you want a copy of that engineering package. And with that, I think we're ready to turn it over to Alan and Richard.
Yeah, I'll take it at the beginning. First of all, I want to thank all our guests. Thank you. It's 5 minutes at the top of every one of these shows. You all give us graciously your time to listen to all the stuff that we have to talk about. So thank you for that. It's important, right? I mean, we don't do this for free. We do it to promote polyethylene. We've got to shout out to the people that help fund our operation. We're very thankful for that. And that allows us to give you all free advice with regularity. But one of the things that we do on these shows is, we don't really let you know who's on the call. So I put this next slide together just to give you an idea of who's on the call today. We had over 250 people sign up today. We typically get about 60% of those. Excuse me, but we've got utilities from all over the United States and Canada here. We even have some folks from Mexico. We're delighted to have them. But for example, Houston's in here. We've got a lot of people in from Houston today. They're the largest user of polyethylene pipe in the U.S. on the wastewater side. On the water side, there's still someone at the utility who believes that polyethylene doesn't cut the mustard for water. So we haven't really been able to convince that individual yet. But still, old habits and old thoughts die hard. And that's one of the reasons we do this 301 show twice a year in the webinar format, because we want people to realize that we're here to stay. The stuff is really good and we have the data to back it up. I also want to say thank you today because we're going 90 minutes. We've got a lot of really good content. Usually we do this in 60. We can't get through all the stuff we want to talk about. We've got El Paso Water. They've come to a bunch of our shows. They're starting to experiment with polyethylene. Flint, Michigan wants some training in fusion. I went out to Seattle last fall and did some training for them. Queen Creek, Arizona's got a bunch of people on the call today. So just a really great response, and we're so thankful to have everybody on board. All right, so yesterday, one of the things we talked about was, what polyethylene can do. We are a solution provider in that we have solved for the typical failure mechanisms of legacy pipe. This is something Fort Worth has not learned. They're not a big polyethylene user. They love their ductile. And look what happened to them in a major freeze event. Hundreds of waterline breaks. They were scrambling, just like the city of Tulsa was. Look at Tulsa's data. They've only marginally used polyethylene for services and small diameter water mains. They don't let it go down roads that are arterials or main roads in the town. How ridiculous is that, with all due respect for the colleagues in Tulsa? we can use it for some things, but not others. This city almost ran out of water. Legacy systems fail in the presence of cold. The reason yesterday we talked so much about seismic activity is because that's the supreme seismic event. When polyethylene's in the ground, it moves with the soil, doesn't break at the joints. Once the system's in, there are no joints, it moves with the soil. Why do you think they use it for conduit on the side of the road? Engineers out there, we have about 100 engineers on the call today. That's consulting engineers plus the city engineers. Are you going to use a bell and joint legacy system for conduit lines or for natural gas? Absolutely not. Why do you use it for water? Thank you for listening to my little speech. Next slide. So, and then today, Murphy Pipeline, you should follow two organizations if you want to learn more about polyethylene in social media. One is mine, because we post every day. When we're not pitching a talk like this, we are educating people with videos and little snippets, little tidbits of interesting things. You should also follow Murphy Pipeline. Their post today, educate a city on trenchless, and you give them cost savings and reduction in community impact tools to implement solutions for a lifetime. So I created this slide that, basically, I love their approach to social media. It's so educational. Do a project, satisfy a need, but teach a method you can make a lasting impact for generations in your utilities. We don't talk a lot in this show today about case studies. That's a separate talk. But what I have learned in the 10 years I've been doing this is that cities that adopt this, they don't have breaks in the middle of the night. Their water loss numbers go way down and their main break numbers go down to stay. Alan Ambler, I'm going to turn it over to you. Thank you to our audience for listening. Guys, best of luck today. Have a great show.
All right. This is me and Richard here. So very lucky to have Richard here on his happy day. And he loves this topic and is extremely passionate about it. So sometimes I have to reel him in, but that's the beauty of being an educator in polyethylene pipe and all things trenchless as well. So we're very passionate about the presentations, the materials, and about sharing that information with you. And we're so glad that you're here with us today as well. So that makes it all better. There is a question and answer section. Feel free to type in the questions. Drew and Peter will be feverishly typing in questions or answers to those questions if it just should be written, or if they want to have us address it live, we can address it live as well. So those questions make everything better. Please don't hesitate to ask away, okay? So enough about us. Let's, here's just a general layout of what we're going to talk about. We're going to talk about the material properties themselves, designing with polyethylene pipe. Will take up the majority of the time for us, and then the resources that are available to you, both at the Alliance for PE Pipe and then Plastic Pipe Institute and other places as well. So here we'll jump right into the material. This is one of my favorite pictures. And Richard, can you tell us what's going on here?
Yeah, so this is an example of a multi-layered polyethylene extrusion that has been butt fused. So it's a cross section of a butt fusion, and it kind of shows the flow of what happens during that fusion process. So you can really, when you take a close look at this thing, and by the way, Alan, it's one of my favorite pictures as well. Everybody thinks that polyethylene, when you push it together and conduct this butt fusion, that all these materials mix together. Well, they really don't. It is laminar flow. But what's really important to understand here is just the chemical bonds that happen between the two sides of the polyethylene in the molten state. So it just shows that that's what you're looking for. There is a transverse direction flow of the material, but it also shows that it's very well bonded together. So it's a really, really important and very descriptive type picture that I really, really enjoy. This next picture is really telling us, you know, if you don't know where polyethylene comes from, it starts at the wellheads that we drill for oil. And basically when we pull all these oils and crude oils out of the ground and gases out of the ground, we'll break them into various components such as methane, propane, etc. But the byproduct of all of this cracking and separation of these products is ethylene rich gas. And then what we do is we purify that gas or that ethylene into a double carbon with 4 hydrogen type component. And then what we do is we inject the catalyst system into it to open up that double bond between the carbons to create these long chains of polymer. So when you open up that center bond, you create a free radical. So we control in the reaction system how long we make those, and that's referred to as the distribution of the polymer. So for pipe products, they have a specific molecular weight that we want to accomplish, and also a range of distribution of those lengths, so we can obtain the performance that we want for water and sewer applications and pressurized systems. So then once you produce that polyethylene in its natural state, it's pelletized. There's some additives that are put in, very small quantities in terms of, you know, 2,000 to 4,000 parts per million, just to protect it against thermal stability, because we're going to heat it up once we get it into our plants, and we're going to remelt it. So we want to protect it against those polymer structures, against any kind of degradation via heat. Just like burning your cake or burning your cookies, it's the same principle. We want to protect against that. You don't want to leave it in too long, but we don't really put antioxidants in baking goods. But we pelletize. It comes to us in rail car. We test the rail cars, then we pop it in our silo, and then we move on to the pipe extrusion process where we add the carbon black, which I'll get to in a bit. Next slide, please. This is a typical extrusion line for pipe. It's kind of condensed a little bit, but way at the far end back there, although it's not a great descriptor, because a lot of people especially don't like showing these pictures that produce pipe, because it's kind of their secrets of production. But anyways, it melts the product, mixes the product, the carbon black, into the natural resin. We extrude it into a profile, which is a round profile, and then we have to vacuum and cool at the same time to obtain the sizes that we want. And the reason we have to put it under vacuum is because if we didn't have that vacuum, gravity would just pull that molten material down, and it would fall, and you would end up with a big U shape. Then you continue to cool it, and then you have the pulling head that literally pulls the polymer from the extrusion die head. You have a wall monitoring system, so you monitor the complete lines of the products made, and then you have the saws that cut it into the appropriate lengths that you require. Next slide, please. Thermoplastics. You know, it's really, I often hear still today, and it is getting better, that people say, oh, it's plastic pipe. Well, yeah, it's plastic pipe, or it's a plastic, or it's a type of plastic, but we have to differentiate our plastics. There's hundreds of different types of polyethylene or thermoplastic pipes, or products that we manufacture, but there's 1 or 2 of those are specifically for pipe. So what's a thermoplastic? A thermoplastic material can be repeatedly heated and softened and put from a solid state to a molten state, so you can reprocess it into whatever product that you want. Granted, again, understanding that the antioxidants we put in there are there to protect against thermal degradation, so we have to make sure that we don't exceed that. And it's about 5 or 6 recycles of that melting that protect it in the pipe world. So anything after that, we basically recycle to other products. And it is reversible all the time. So you can, just like a candle, you can heat it up again and stick it together. It's the same kind of principle. That's just a low molecular weight polymer is all that is. A thermoset material will actually cure. So once it cures, like an epoxy or a silicone or a polyester, they will, once they're cured, then you cannot remelt them, and they cannot change that structure back into this. That's the solid state that they have. And that's the really basic generalization of thermoplastic versus thermoset. Next slide, please. Here's a little video of the fusion process after the heater plate's been removed. The surfaces are nice and smooth and clean, and then the rollback bead forms on that polymer. So just like that initial picture that we showed you, that's what's happening. The material, when those forces come together, force that material to the inside and outside of the polymer, but the design of the pressures that are used and the cooling times, etc., are all based on maintaining that interface where those polymers will actually chemically bond together. So that's the fusion process, and that's the jointless or the monolithic system that we create once completely cooled under the regulated procedures. Polyethylene is a semi-crystalline product. So it's about 90%, 85 to 90% of the structure is crystalline. So the best way to describe this to keep in everybody's head, if you're not familiar with it, is a kid's ball pit. So you have all these balls that are in the ball pit. Those are your spherulites, or those are your density or crystalline regimes. So what happens with these long, 175,000 to 320,000 carbon length chain is they have an affinity to one another, so they fold over on each other. So if you look at the picture of the crystalline region below, what you're seeing is kind of just a cut face out. Well, that crystalline area is a spherulite, it's round. So you have to picture these rounds, and then what these spherulites have off them is fibrils off of the side, so they will attach to one another and they'll cling to one another, which are referred to as tie molecules. The other one, the amorphous regions, which you see in the crystalline structure, so that's the areas kind of between all the balls that you have in the ball pit. And by the way, when we design polyethylene spherulites for pipe products, they're all the same size. You don't have basketballs and footballs and baseballs and ping pong balls all mixed together, because your amorphous regions become larger. And so those amorphous regions are kind of susceptible to your slow crack growth, which we've improved over the last 10 years immensely. So now with that ball pit, with that all those balls that you can kind of move between, so the kids can go in and they can dive between them, just like a reagent or a chlorine or an oxidizer or whatever, or a hydrocarbon, they can get through there quite easily, because it's very mobile. Those spherulites are kind of mobile within it, which makes it the viscoelastic material that it is. So anyways, what we've done now is taken those spherulites and added Velcro to them in the current PE 4710s. And that's really good to understand, because that gives us our flexibility and ductility. Yes, Alan.
So that spotlight on innovation is something that always amazed me, as being a civil engineer, environmental engineer, looking at this pipe product and how it's developed. So talking to a chemical engineer such as Richard, that is so passionate about this process, it was always amazing to see that the actual material properties have just been developing into a fourth generation, something that is even better than when it was first invented. So that innovation has always amazed me, and I love to hear Richard talk about it, and I'm sure you guys do too. So it's pretty amazing what has happened over development of this material itself.
Yeah, that's right. And it's not saying the third generations are all that bad. It's just we just made them a lot better. And you're absolutely right. And the key thing to that, what you're going to hear, is just the difference between unimodal reaction and bimodal reaction. We have two reactors instead of one, and they're linked together to give us the properties that we desire. You can go to the next slide, please. So being a semi-crystalline polymer, it is rubbery, it's ductile state, but it's for polyethylene, the ductile state is very low. I mean, you have to get to minus 130 degrees Fahrenheit before you reach the glass transition of this product. So any kind of operation underground that we have for water or sewer, even when it was minus 40 up here and minus 12 in Texas, it's mobile and it's viscoelastic and it'll be able to adapt to it. Doesn't mean that it's collapsible in a lot of cases, because we've designed the strengths to make sure that we resist the burials and the burial requirements that all of you guys have for designing your pipeline systems. So we have better toughness now. We have better impact resistance. And the impact resistance is good, but it's not invincible. I mean, you can still gouge it with a bucket and you can still do things. The other aspect of this is the slow crack growth potential. So any kind of permeation or reagent going through those amorphous regions has really, really been improved so it doesn't happen. And also rapid crack growth you'll hear as well. So when products do become colder, or polyethylene does become colder, it has a higher resistance to impact type failures and cracking because of the improvements we've done to the joining those sphere lights or that technology together. It has a very sharp melting point. This sharp melting point means it gets to a certain temperature, it absorbs heat, absorbs heat, absorbs heat, and then all of a sudden it can't hold that heat anymore, it just releases it. And that's about 135 degrees Celsius. So it's very sharp, and it'll go from a molten state to a solid state and vice versa in those aspects. So really, really important to kind of understand this, that these new technologies of PE 4710s have really stopped the cracking process. And that's a real key. Whereas amorphous polymers, such as PVC, where you can think as they're not really long chain branches, they're more of a bond between additives that are put together and grainy substances, that meld together. So there's no entanglement. There's no real joining and chemical joining between those surfaces. They just come together, cure, and then of course are more brittle. And so for an amorphous polymer like a PVC, you're up around 121 degrees Fahrenheit, whereas the ductile transition. So meaning that it's in brittle state when you're utilizing these products in the ground. They got great strengths, they got great applications, they do have purpose, but that's the key difference. They don't have that ability to handle any kind of movements or any kind of sudden sharp impacts or stress loading on these products. Next slide, please.
So Richard, as kind of a lay non-engineer person trying to understand the primary difference between a polyethylene and a PVC, to me, it's two things. One is PVC is brittle, but the second thing is it suffers from cyclic fatigue and we don't. So can you explain why we don't suffer from, we're both plastic, so why don't we have a fatigue issue over time, and why do they?
Yeah, well, it's the ability to move. It's the viscoelastic behavior that we'll touch on a little bit later in the presentation. But it's important to really understand this, that we have that ability to move. So the forces that we apply to such as a surge event, which is a water hammer event, is a very violent event when it comes to either absorbing or propelling that energy further. And for in rigid products, so in rigid or stiff or brittle type products, they will convey that energy, whereas polyethylene will actually disperse it. And that's why we don't fail in that fatigue mode, because it's actually dampened. And that's probably the best way to describe it. When you look at this slide of the modulus, the apparent modulus of polyethylene, we don't just look at short-term modulus at 150,000 PSI, where PVC is 400,000 PSI. So you may say, oh, hey, I got way more stiffness in the PVC than the polyethylene. Absolutely true. So what we want to make sure is how we understand that and utilize it. So we looked at stiffness was a problem in polyethylene in third generations, because the more we increase the density to increase our modulus strength, then the more brittle the product became and more susceptible to cracking and either slow crack or rapid crack growth, just like brittle materials are. So you'll reach a point where that stress will overcome, and then you have catastrophic failure. Whereas polyethylene just does not have that fatigue mechanism. So what we look at is we look at the instantaneous modulus, but we also look at long-term performance. We want these pipes in the ground to last greater than 100 years. So we use modulus of long-term to understand what we can handle. So we actually derate it and understand that product.
So when I look
Alan.
at this graph, Richard, one of the things that I see is it speaks to the durability of the pipe while handling it. So a very important thing in trenchless technologies are the forces
Absolutely.
that the pipe undergoes while it's installed, and being able to take some of the abuse that a contractor would give to it within a pipe bursting standpoint, and this changing of that apparent modulus of elasticity really speaks to it. So it's just numbers right now. We're going to show you exactly how this translates a little bit later in the presentation. I love, a good photo is worth 1,000 words. A video is worth a million. So we're going to see some of that as well. But we're okay.
Yeah, great point, Alan, and it is important. And you can go to the next slide, but there's design in any installation process that along the way as well. I mean, we want to make sure that even the design, when it's the design engineers have it on a table and a piece of paper and they're looking at it and they're putting in all the criteria that they want. We want to make sure when it gets to the handlers as well and the guys that put it in the ground that they understand what it can do as well. And that's exactly right. That's a very good point. We want them to understand that there are limitations and we don't want them to have problems. So all polyethylene materials have a designation requirement. And over the years, these designation requirements, which are controlled by ASTM D3350, which is the cell classification. So there's material classifications and then there's pipe classifications. So we want to make sure that we hold up both of our bargains from the manufacturing standpoint and the pipe standpoint as well. So we clearly understand and provide the proper information to engineers so they also properly. So you'll see these on the print line, which is the PE 4710. If you go to the next slide, the cell classification, the long term is all of those items that you require in design. So the short term, which you'll always see in the on the pipe print line, is the material type, the density class, which in this particular case 4 is 0.947 to 0.955, so just below the 1. So that means the product floats. Then also the slope crack growth performance, and the reason the slope crack growth is so important is because it's changed over the last 10 years, or these 2 generations of products. It was pretty good in the 3408s and 3608s, but it's really outstanding now in the 4710s. It's to kind of give you an idea of having a reagent penetrate that amorphous area. So the kid going through the ball pit, if I stated that analogy, what you end up with is 1 hour of pent is equal to 14.1 years of service life, according to Dr. Norman Brown, the inventor of the PENT test, which is the Pennsylvania Notch test. And it's a stress-related test over time that fails the product to understand that what the resistance is of slow crack growth failure mechanism. So that's what we're really looking at, is that failure mechanism. The last 2 digits are the hydrostatic design stress. So that incorporates the 0.63 design factor already. And there's always discussions about the 0.63 design factor because they're not safety factors. We build into the HDS from the HDB of 1600 in this particular case, because 1600 times 0.63 is 1000. And so what we build into that is handling in the field, scratches and gouges and things like that that are kind of out of our control. So we've already built in a safety, so-called safety factor into the design factor. And then engineers can add any other kind of safety factors they wish to add comfort level to their design. Next slide, please. Hydrostatic design stress is really depicted here by a log-log relationship between hoop stress and time. And these log-log relationships are very stringent. This process is developed through PPI policy of the Plastics Pipe Institute. And the Plastics Pipe Institute has what's called the Technical Report 3 that gives the criteria to establish these curves. So negative slope curves, so you can see the blue line with the failure points on them, and those are failure points. And we require failure points in each decade of time in order to create confidence in that data, so we can project either to 11.4 years or even 50 years, depending on the failure mode. So what happened in the past with older generation polyethylenes at about the 1,000 to 10,000 mark decade, failure mechanism would change. It would go from ductile, which would be an expanded type beak failure, to a brittle failure, which was a transition. So what would actually happen to that curve about 10,000 or 1,000 to 10,000 hours, you would take a drastic hinge downward. So then you would have a two-type regression curve. So what they've done with the new 4710s is eliminated that, what was referred to as the knee, the curve of the knee, which is not demonstrated here. But once we establish that ductility and also the hoop stress capability of the polymer and the pipe that's produced, then we can regress this line with a high degree of confidence with a minimum degree of LCL, which is your lower confidence limit of 90%. So though that data scatter has to be very tight like it is, and if you have one data point that's way out there, you really don't have a methodology to understand it unless maybe a poor fusion on the caps or how it was held. That's the only way you can define that or remove that point from there. Other than that, you have to go to statistical analysis to remove that data point. Next slide, please.
Well, before you go there, I have a question for you. And I've heard you say before, Richard, that that slide is the reason that we're all here. One of the questions we get as a background to your response to my question is, we have people asking us all the time, well, how do you know it really lasts 100 years? And I say, well, how do you know it for any of the three pipe types? Because we all say we last 100 years. But for us, Richard, that slide is it, right?
Yeah, that is part of it. It's not a life expectancy slide, although it is time-based. So you don't predict life on that. You look at life in terms of your whole system. But the system itself, and when we look at these regressions, the confidence has been very, very good. The science and engineering behind the policies that were developed for establishing these curves is very, very good. And we're very confident as an industry, not just me as a pipe manufacturer or a resin manufacturer, but we're very confident that this process works because now we're starting to get history behind it as well to give us even further confidence. Although, you know, we've got pipe in the ground for 63 years, these predictions or these regression curves to establish that hydrostatic design basis or hoop stress capability is very, very good, and the confidence is very, very good. And you know, there's always discussions in the industry to how we can better this or change it, and we haven't changed it for a lot of years because that's how confident we are in the math and the science that backs that performance. Operating temperature, again, I just want to say to you that, yeah, it can be installed in colder weather conditions as well. We do have limitations when it comes to the fusion process. We'd like to be able to heat, you know, minus 20 Celsius is really an area where we start to question. So you have to tent and heat the ends prior to fusion because the pipe just gets so cold. It'll take on that outside temperature, so it just takes longer for the heating cycles to work through it. So again, the glass transition for polyethylene minus 130 degrees Fahrenheit, not an issue. It stays ductile. Does it become stiffer in colder temperature? Absolutely, because it's condensing. It will shrink on itself, so it becomes a higher density. So the energy to bend it will become higher, but it does not change your bend radiuses that we'll talk about a little bit later. Next slide, please. Oh, and here are the graphs. Yeah, just I think we've seen them already in the earlier, but that's just showing amorphous materials versus brittle. So you're ductile. Your product is ductile, so it can handle this. We insert this slide in here for the materials because these Tubbs fires in Santa Rosa, California, really created an interesting development. They had few water lines above ground that were placed in ground above ground because they didn't want to disturb the forest or the green spaces that they were going through. So they left it on top. Unfortunately, the green spaces burnt, and so did the polyethylene. And there were some accusations, I guess, around benzene generation, where polyethylene does not generate any type of benzene. It's a benzene, it's hydrogen and carbon. The benzene was from external sources that were found at a later date. So those studies have been conducted, and you can read further on these observations by PPI. Yes, Alan.
One of the most interesting things about the fires that were analyzed, Paradise Fire as well, is the actual operation of the distribution system was one of those freak things that really pushed that infrastructure to its complete limit. So if you can imagine, as quickly as those fires moved through these regions and areas, the firefighters were trying to fight it on one side of town, and it's moving as quickly as possible. They're trying to fight it on the other side of town. So something that may have burned down within the infrastructure no longer needed that, but they needed the water at a completely different location. What that did was create a vacuum in multiple places within the distribution system, in which case the extreme need for water sucked that burned material into the pipe network. It's very, very clear, and I want to make sure that everybody understands this. The buried polyethylene pipe that has at least 12 inches of cover, we obviously typically want 2 to 3 feet minimum in different places, was not harmed at all in any of these fires, because most of that heat is absorbed within the top 12 inches of the soil column. But it was the actual act of a vacuum that pulled foreign debris into the water system that then subsequently made a chemical problem within the pipeline itself. So that's an interesting analysis, and of course, we don't design for those types of things. So the concept of polyethylene releasing this benzene is it needs to be very clear that that's not what happened. What happened was a situation that pushed the polyethylene to the distribution system to its absolute limit, and then created a vacuum as to which absorbed that bad content.
Thanks for the explanation. I'm glad you guys put this slide in here. Just a couple points of fact. One is Richard brought up the burning of polyethylene pipe at grade. That was San Lorenzo Valley Water District in, I think, October of 2020. They subsequently put polyethylene back in the forest that burned to resupply the water tanks. And secondly, Richard and Alan also talked about Paradise, California. That was a fire that was 2.5 years ago. And they subsequently have put polyethylene back into their system for mains and service lines, as published by the Plastic Pipe Institute a couple months ago. Good job, fellas.
Yeah, thank you. Yeah, it's important, guys. If you hear things like this, please contact your local manufacturer of the polyethylene, or and then we can direct you to the doctors that build all these polyethylenes and things, and we can help you out, get the right explanation for the product. So for design, of course, in this short time, I can't cover every aspect that there is in design, but we're going to cover the main points. If you have any other questions, please put them in there and log them, and we'll address them either live or at a later date. But dimension ratio is very important for establishing your working pressure, because the thicker the polyethylene or the lower the DR number is higher the pressure. So it's just that simple. So DR divided by the OD divided by the minimum wall thickness that we have on all the charts for producing it. And they're either made to iron pipe sizes or ductile iron pipe sizes. So for example, a DR11 is rated for 200 PSI in a 4710 material, and a DR17 is 125 PSI working pressure. And this is really important because it applies to everything you want to understand in your design to make sure that you can handle the operations of your systems. Next slide, please. Again, we have to emphasize, because polyethylene does soften as it heats, if it does get warmer, or you do want to use water in a hotter environment, or some kind of interface, whatever you're transporting in a hotter environment, we have to derate. We have to derate that pressure capability, because if you're softening the material, it's going to have less ability to hold hoop stress. And hoop stress is basically the middle of the wall, is how that forces are applied when we pressurize a pipe. So as you can see in this, pressure rating is equal to 2 times the hydrostatic design stress, which is now 1,000. And then we also have the AF, which is the environmental effects. So if you have water, let's say in the oil field with a transfer that has hydrocarbons greater than 2%, then we have to derate that as well. And we understand that, although we don't have that chart shown here, because for you guys, it's water and sewer, and that does not really apply. And then also the temperature of the operation of that line divided by the DR minus 1. And that will give you your pressure rate. So it's a fairly simple calculation to determine what that DR11 200 PSI is. If all factors, including environment and temperature, are 1, then you'll end up with 200 PSI. But you can design for anything over that 80 degrees is considered ambient as well in that picture. 81, you'll have to go to the duration of that aspect. And that's why we put 81 on there. Now, if you go colder, it'll actually get more, have the ability to hold more pressure because it's more dense. So you need to understand that aspect of pressure rating. Next slide, please. Surges, like Peter said earlier, we don't have this fatigue issue. We don't fail by fatigue because we understand that surges are part of water operations and pressurized water operations. So we needed to understand it. So we needed to look at, well, how does this temporary fluctuation in operating pressure when a valve closes or power shuts off and the velocity of the water changes in that few seconds, what's that effect? So we kind of looked at it in two different types of surges. We looked at it as one is reoccurring. Reoccurring can be like a regular surge event, which is pump on, pump off. And typically for municipalities, it averages across the nation about 55 cycles a day. And then also occasional, where maybe this pump system is pulling raw water, and it stays on all the time, filling up these tanks. So then the power shuts off. So it's an unexpected or not a regular event. You can be 2 times the pressure rating to be able to hold it. The reoccurring will be 1.5 times, which I'll touch on in a bit. But we really need to understand the conditions of what surge pressures are and the magnitudes, the allowance, and also the fatigue resistance, which is the other failure mechanism for our piping systems. Yes, Alan?
In recent years, there's been more effort to be able to understand transient surge pressures as well on a very, very small scale in the millisecond. So that pressures sometimes far exceed what we're talking about in 1.5 and 2 times, and the ability of the material property of high density polyethylene to absorb those really helps dispel that any type of transient pressure. So those typically are seen right at where that change in velocity is occurring. And a lot of times municipalities have gone to a high density polyethylene outside of large pumps or other things of that nature in order to be able to try to absorb some of those pressure transients as we go through it.
Yeah, and yeah, you're absolutely right. And it's every potential failure mechanism and that we have. And this is what relates to Peter's comments on the solution. We don't want to have problems in the future with underground. And there's lots of other additional causes that we may or may not have taken into account, like ground soils and how they shrink and contract when they're moist and wet. So we also look at those as well. So just go to the next slide, please. So when we look at these surge magnitudes, for example, it's related to what our modulus of our materials are. And so when you look at these two factors of velocity change and the modulus of elasticity of the products, sometimes velocity change is not equal to the same surge pressure. And that's evident in the graph to the right, where we have surge pressure of a certain volume, but we also have the material type and size, where how this modulus negatively affects that magnitude of that surge event occurring. So you can see that because of the dampening effects of polyethylene on the lower modulus, you see a very low effect of the surge. And so lower modulus actually equals lower surge pressure. So if that's the case, then you're actually building in an automatic safety factor into these products. Next slide, please. So when we look at these values, we go, okay, well, how do we measure this and how do we protect against these surge events? Well, typically what we've done in the past is we put some kind of design factor or dampening factor to protect the higher modulus materials, such as PVC. You have a one-time 1.0 times the pressure class. So if it's rated for 250 psi, you multiply by 1, well, it's still 250 psi. For occasional, they can boost it up a little bit because those events, those rigid materials can handle it a bit better. Whereas the ductile iron has always had just this plus 100 psi occasional and recurring factor into this design. But the interesting thing about reoccurring and occasional design, if you can design it either way and how you want to do it, we don't have really a negative effect with these surge events because it's actually a multiplier of 1.5 and 2 on the pressure class. We actually have higher pressures that we can handle even if you have these bad surge events that occur, and you'll be protected for the lifetime of that product based on these operating pressures that you see on this graph. So we're protected, and so you can be reassured that you're not going to have failure. Next slide, please. And by the way, all of those results can be calculated in comparison with the PACE calculator at PPI. That's where those numbers all come from. And that's the whole industry put those together, by the way, not just us, the polyethylene department of plastic pipes. It's all plastic pipes. Fatigue resistance, again, is something that we thought that if we can solve this issue, then you guys are going to be protected in your design. We'll look at your top loading, we'll look at your dynamic loading of H20 loads or railroad or anything like that, because all these questions now are coming up just because we've resolved this issue. Now we have to make sure everybody's clear on it. But high density can handle up to 15 million cycles without any fatigue failure. Well, if you take that on your system, which averages about 55 cycles a day on the water, you've got greater than 100 years associated with that as well. So you've got lots and lots of fatigue resistance, and that's why we don't see these failures. Ductile iron, it's not factored into the design. PVC can only allow a certain limit of velocity. And this is where the ID issue is coming into play, because we have existing PVC lines in there. We want to match the ID to the connecting polyethylene. Well, you really don't have to if you're moving from PVC to the higher velocity polyethylene and then connecting to a valve and done. You don't need to reduce it because polyethylene can handle velocities up to 25 feet per second. Whereas I think the limit for PVC, and don't quote me on this, but I believe it's 6 feet per second, which your typical operating system for a water is anywhere from 4 to 6 across the nation in terms of what we studied for 455 different municipalities. So it's all good information. We understand, that pressure during that surge event, and we want to make sure that everything is protected, including the valves and the connections associated with that system. Next slide, please. Yeah, this is again directly related to your IDs of the scheduled pipe and cement. PVC and polyethylene have the same Hazen-Williams factor for the product of 150, so they're comparable. So we look at the other products, the other generations of products, but one of the things that really stands out when we were doing this is that polyethylene ID doesn't change because of any kind of tuberculation that occurs, which would definitely affect the Hazen-Williams effect of a new cement pipe or steel pipe. Because as it builds up, that's going to become reduced and your ID is going to become reduced. And you can see in those pictures after 9 years and 6 months and 41 years for polyethylene, there is some rust, just like the other water lines that were removed, the steel lines that were removed there. That's just the iron content. But you can see that little scratch on the top there. That was just a fingernail that really put it off, and that's 41 years later. So think about, and that is an electrofusion profile that you're looking at 41 years ago. So we're starting to get a lot of confidence in how we do things. But what's really important here, not matching ID, what is your flow rate requirement? So if you have a flow rate requirement for polyethylene and you're not going from, let's say, PVC to polyethylene to PVC, then you don't want to have a higher velocity that's going to cause problems with the PVC at the other end. You have to design that properly. But the key is just let the math do the understanding for you, that if a narrower ID, such as this example of a DR17 with an ID of 11.55, and the other two products of steel and concrete are a larger ID, you basically have the same flow rates. Why do you need to change the ID and adapt for that? So that's one of the things that come out. Let the math do the work for you, because it's what should be doing the work for you anyways, because it's the science. Next slide, please. So chlorine resistance is also a huge consideration in water systems, because we have to put disinfectants in our water so we don't start to have people getting sick or dying from infections that can form in a water system. So one thing you have is, one, you don't have buildup and contamination, so it's always kept relatively clean in a polyethylene system. But what we did is we started to look at how these chlorines and chloramides can affect what's referred to as the PDI, which is the pipe disinfectant index. And so the science behind this is huge, and there's all kinds of reports that are put out that you can read and understand to help you understand this PDI, which we created a cell class for this particular polyethylene, which is called either a CC1 or a CC2 or a CC3. So it's a chlorine resistance test that's done. But we take into consideration in this PDI calculation your annual water temperature, or average water temperature, sorry, because that can change over the year. And if you wanted to use the high or the low, it doesn't really matter. If you're going to wanted to look at worst case scenario, take your high. The operating pressure of that system, the residual chlorine in that water, and also the CC level that I described earlier, and the OD of the pipe. And it'll give you a PDI. And anything that has greater than or equal to 1 is 50 years of resistance or more. Anything with greater than or equal to 2 will give you a resistance of 100 years. And this is another aspect that gives us the 100 years that we have science and testing to back the performance of this product. So again, going back to what Peter said, your solution. Next slide, please. Disinfectant index, again, this is kind of to show you how we put it together and some examples of the calculations. But this was part of the surveys that were done across North America. I think, like I said, there was 455 utilities looked at, but all the working pressure, everything that was associated with it. So a CC2, which was the 3rd generation product, and now a CC3, which is all the 4th generation products and the 4710s now. So they're all CC3. So you don't have to ask for it, because you already have it, because we can't get, as a pipe manufacturer, the older generation products anymore, because why would we? So it just gives you an example of all of these are greater to or equal to 100 years. And through the calculation, I can tell you it's a lot more than 100 years. But we're being very, very conservative from an engineering standpoint, and also a practical standpoint, that these things need to be calculated, and they're easily understood. And you can go on to the PPI website, and there's the HDPE app that you can, if you look at pressure application, an automatic drop down will come down, and it'll look at oxidation, and you can put in those values for yourself and calculate your own water system. Next slide, please. Hydrocarbon contamination is a huge bone of contention, because we have, in not only the US, but Canada, we have old gas stations that used metal type gas tanks underground, and we have these plumes of hydrocarbons, and people are concerned that this hydrocarbon will permeate the polyethylene and contaminate the water system. Well, Purdue University developed a calculator to look at not only the rate of the permeation, but also will classify it, the soils, because you'd have to do analysis on the soils to see what's really in there, and then they would tell you how long it will, or what percentage of level of hydrocarbon would permeate over a certain amount of time. So a lot of science and work went into developing these calculators, which, again, we understand it, but if you don't want it, because hydrocarbons, the BTEX products can permeate polyethylene. But remember, we are primarily used in the hydrocarbon transfer and gas systems for oil and gas gathering systems. So we understand this. It doesn't necessarily negatively affect the performance of the pipe, but you don't want that contamination in your water. Yes, Alan.
So one of the most interesting things about this analysis, most of the work was done to be able to look at the remaining strength of the pipeline, if it is placed in a hydrocarbon area or contaminated area. But as civil environmental engineers, if we know about an area that has that ground contamination, we're going to want to rectify it as it stands anyway. So we'll want the opportunity to be able to fix brownfields if possible. Yes, it does take time and it costs money to be able to do so. If it's not possible, then we will double wrap that polyethylene in and of itself. So that way, that system will have a polyethylene pipe within a polyethylene pipe. Those are actually most common in landfill applications where they're moving leachate around. So that's the primary pipeline that is used in landfill applications where they know that they've got some chemical movement and some issues with it that need to be rectified and changed. So yes, hydrocarbon contamination can move along the pipe wall, which is an interesting aspect to think about polyethylene. With other pipe materials, it does move along the gasket. When you put that pipe in the ground, and you've got to then be able to try to make sure that you double wrap those pipes as well. But typically, we would not put it in a contaminated zone if possible. And this is here really just to show you that we have the science behind it.
Yeah, and that's right. And dual containment, if you don't want to, if you're okay with leaving that plume there, I mean, dual containment through that section is very easily done. Whether it's 100 feet or 1,000 feet or whatever, it can be very easily done. And then you can go back to the single layer and you won't have that contamination. Next slide, please.
Yep.
I think we're getting close.
That's it. That's it. So that's
it for me.
That's one of my favorite aspects of talking to Richard and many people like that, is to see just how much goes into making this product. I did an entire presentation with a gentleman on testing and the different things that you have to do while testing in the manufacturing plant to see this. And it's pretty wild what ASTM standards actually require Richard and his people to go through in testing the product. So that gives me an absolute comfort level as a civil environmental engineer to be able to call for this product to be able to be used in all of the traditional installation methods, as you'll see here. So open cut construction, HDD, pipe bursting, slip lining, compressive fit lining. We're going to talk about that, which actually temporarily reduces the OD of the pipe while we put it into an ID of a pipe that's actually smaller than what that HDPE pipe would do. And then it's allowed to regain its shape and forcibly pushes up against the existing pipeline. You would do that in pipelines that cannot be pipe burst, such as pre-stressed concrete cylinder pipe and other pipes that are heavily reinforced. Then we'll talk a little bit about marine installation and plowing. So for the next one here, actually installing a high density polyethylene pipe through open cut construction is no different than what you would do with a ductile iron pipe or PVC pipe. Those are actually considered to be flexible pipe materials as well. So we want to make sure that the bedding is all sufficient and proper to be able to have no rocks or other things that may very well damage that pipe and embedment and then start to build up from that material and good material. One of the most unique things about high density polyethylene, because you can fuse long runs in advance, is in a brand new development type of standpoint. So if you have the ability to open cut long longer sections undisturbed that are in a safe manner, you can install a significant amount of pipe in one shot. And this, when you're constructing in dense urban or suburban environments, you don't always have that luxury, especially if you're crossing a main road or something like that. They typically are limited to 100 linear feet per day of install. But this concept of a fused run, strung out and advanced, with lots of room to be able to put this pipe in is shown here. This is a municipality in Austin, Minnesota. They tell their residents in the neighborhood, hey, bear with us for a little while, and then we'll be able to install all of the utilities all at once and then repair your road as we go through it. So they cut very long runs up and string long runs of that HDPE pipe up above ground and then install it all at the same time. There's a pretty big difference when we're looking at trenchless technologies, which is a field of installation technologies for less trench. So typically they can get into 85 to 90% less excavation than traditional open cut. And what you'll see on the right here of the screen shows exactly the path line of a replacement pipe that we're looking towards. And the small size of the pipe, the excavation pits that actually are dug. So that's what we talk about when we talk about trenchless technologies. So direct burial, what we're looking for here is deflection limits, constrained, collapse, and crush. So we really, the time period as to which you're handling that pipeline to put it in is going to be one of those where it might experience the most stress during that installation. So you want to make sure that you've got ample room on either side of that pipeline that is properly compacted. And then we don't have any rock impingement on top of it. We have good backfill as we go through it. And when they do perform those compaction activities, that pipe is well protected as they move up in their compacted lifts. So again, you would do that for any type of pipe material. But the strength of PE speaks to this durability as we go through and install it as well. Oops, there we go. Two biggest factors in design equations for direct burial pipe are that modulus of soil reaction, as we're looking at, and we want to make sure that those are distributed directly to the soil, as any forces that are exerted on the pipe itself are distributed through the soil. So that's the same concept as installing a ductile iron pipe and a PVC pipe as well. So that's why they call it a flexible pipe, is because it distributes those to the soil as it goes through. Most of these are installed in a standard design window. So we're looking at that 2 feet to 25 feet maximum depth of cover. You can install polyethylene at much deeper limits, and then you'd have to look at that soil column above it. I've heard of installations well in excess of 100 feet as we go through, and the pipe can withstand those installation depths as well. So if you're in the 2 foot range and we're looking at special loading scenarios, so that's I've had to look at polyethylene pipe on the side of an embankment as to which they would have a grade all on top of that embankment. That would be a special loading scenario as to which you would look through and do actual calculations. The information is there. It's available to you to perform those calculations in the Plastic Pipe Institute Handbook on Polyethylene Pipe. And it's seldom that I have actually had to perform that calculation, but those are special loading scenarios as to which we would look. Okay, excuse me. Thrust blocks. We get this type of discussion all the time on exactly when you would need a thrust block. So polyethylene pipe is a self-restrained monolithic system. So what that means is if it's all polyethylene from the very beginning to the very end, then you don't need any restraints in between. What we're looking at for the need for thrust blocks is when we're connecting to a legacy system that has bell and spigots, and then you would subsequently have movement within that polyethylene pipe and then be able to pull that pipe that you're connected to out of the bell and spigot connection. So the types of restraints that we're looking at for that, then this electrofusion restraint that you electrofuse onto the side of the pipe, a butt-fused wall anchor, those things are then embedded in concrete to be able to make sure that no movement on the downstream side of this polyethylene pipe. There are typical details within the Alliance for PE pipe engineering package that you can look for to be able to make this happen for you and understand those calculations. So Poisson's effect, when that pipeline is pressurized, what we see is we see internal pressure that happens within that pipeline, and then we get slight change in the shape of the pipe. So it can withdraw some. So that's what we're restraining when we're connecting to a legacy system while that pipe is happening. So that pressurization of that system then obviously shortens the length of the pipe, not by a substantial amount. So that's what's most interesting about the molecular properties of polyethylene pipe is while it does exhibit these behaviors, the actual force required to restrain them is not substantial. So this is just more graphics and showing you what is happening while that pipe is pressurized and moving through, and then exactly where that material is going. So we look at temporary conditions. This is an above ground application, in which case you would temporarily or restrain that pipe from lateral movement, as you see in the right picture here. So that way it doesn't snake all the way through wherever you're going through it. So you want to make sure that it doesn't push out into a road if it's a temporary bypass along the side of the road. And then we have anchored and guided systems for more permanent installations, such as on a bridge and other things. Richard and I will be talking about above ground installations in significantly more detail next month, which we had talked about before. Yes, Richard.
Yeah, I just had a quick question. Instead of writing this one out, we had a question regarding connecting to asbestos type pipes to polyethylene. I said, do you want to give any guidance to what you would do there? I know you burst all your asbestos pipe when you were in Castleberry, but what if you had to connect to it?
Okay, so AC pipe itself, as it nears the end of its service life, becomes more brittle. They were 13-foot sections of AC pipe and bell and spigot itself. So safe handling practices of AC pipe in the field show that you would not take a cut saw to the pipe. So if you expose that pipe, you would keep it wet and put a burlap bag over top of it, break it, and then you could pull it out of its segments as we go through. When you're connecting to it, you would use a mechanical adapter, such as a Megalug or something of that nature, MJ adapter, to put up against that AC pipe, and then you would just connect to it in a similar fashion. That's all bell and spigot pipe that way. You essentially want to restrain that joint from being able to pull it out as we go through it. Now, you can pipe burst asbestos cement pipe in accordance with all the regulations that are part of the national emission standards for hazardous air pollutants. Typically, people that don't understand what pipe bursting is hear pipe bursting and asbestos in the same sentence and envision fibrous release into the atmosphere. That's not what happens. Since it's a trenchless technology, it makes logical sense to keep 90% of that pipe buried and not expose it, since the industrial hazard of asbestos happens to do with breathing and inhalation of the particles itself. But we got a little bit off topic with the asbestos. Just the restrained joint is what you really need to be able to connect to it. Thank you for that, Richard. I appreciate it. So again, this concept of movement along the thermal expansion or Poisson's effect, I really wanted to hit home, and this explains why high-density polyethylene is a monolithic system and self-restrained. So even though this temperature that we see, a change of 40 degrees Fahrenheit above ground, would change the length of the high density polyethylene 8 inches versus a carbon steel pipe only 3/5 of an inch. The actual force required to restrain that is significantly less. So that plays into this entire concept for you to understand that any movement within this pipeline system that may happen from surge pressures, from Poisson's effect, from any type of thermal installation coming from above ground initially into below ground there, it takes so little force to actually restrain it that's why it is a self-restraint system. Very impressive to me what happens from this pipe from a material property standpoint. They have all the calculations within PPI to be able to understand this, just how much it changes, and everything that you need to be able to prove that to yourself. So horizontal directional drill is typically the gateway to be able to start to look at polyethylene pipe installation. Very prominent pipe within use of HDD itself. HDD, the allowable bend radius is not the limiting factor for your HDD curvature profile. Oftentimes that's the drill string and the capabilities of the machinery, the entrance and exit pits or exit angles in order to be able to control it. So within the borehole itself, a high density polyethylene could float. The same thing in marine applications, it does float. So we want to make sure that we put either water or some fluid within that pipeline to make sure that it's centered into the borehole. And what that'll do is allow us to ensure that we minimize the friction around the path of the pipeline here. Richard, why don't you tell us what's happening in this video as we take a look at one of the largest HDD applications. This is a 54-inch gravity pipe that was installed in the city of Miami Beach here. I'll play the video as well too.
Yeah, no, this was one of the largest. The city decided that, they had a severe leakage problem with sewage, of course, in Palm Beach and this whole area, Miami Beach area. That's the last thing you want in this particular area, especially when tourism is your number one economic driver. But they did this 4,200 feet, 54-inch in 2 segments, and drilled it under the streets, which you can see in the distance there. This is the 2 pipe strings that they had. So they literally, once they started the drill, and they pulled back. So the drill would be at the other end of this thing, pulling this pipe back through the city under the ground. I believe the total installation only took about 24 hours. I can't remember the time. There was a significant cost savings because you don't have to dig up all the streets. You don't have to create all those delays in traffic. The traffic still flowed beside the equipment. One of the complaints was noise in the evenings because they needed to run it. So they put up sound barriers to help the local residents dampen that noise. So quite a significant design and engineering feat for polyethylene. And yet this line, once they got it done, literally saved them millions of dollars because they didn't have to chop up all this infrastructure, a pit in and a pit out. They did have to stop it, the process, to refuse the 2 pieces together because they just didn't have a long enough staging area for the total 4,230 feet. So a really, really huge accomplishment by that group in Miami. And to this day that I know, they're still ordering and utilizing polyethylene to its fullest.
Okay, so it is a very ductile pipe. The bend radius is shown here, and it essentially allows us to really change and move this pipeline in the field. So that's that temporary elastic modulus of elasticity that we had talked about before in the behavior of the pipe during a temporary loading condition. So it's extremely forgiving and allows us to do things like this in the field. We do need to look at lower or higher DR ratings for a lower pressure pipe to make sure that we don't end up in this scenario here where the contractor over pulled this pipe and then stressed it itself to where it kinked. So this is what we show just in field applications itself, how we can, through a pipe string that was pulled into place prior to a pipe burst, allow the anyone to move through this. So of course, this is not in the technical specifications, but it is something that the contractors can often do in the field to be able to provide you with durability of that pipeline. So safe pull force, we look at the borehole friction. These are calculations that are available to you within the Plastic Pipe Institute Handbook on Polyethylene. ASTM does have standards for you as well that help certainly understand all aspects of horizontal directional drill design. So we're looking here at really within the HDPE pipe, we're calculating the friction forces at the primary components of installation that you would see within a HDD profile, and we're making sure that the stresses within that pipe wall can survive the stress and friction that a contractor would see while they're installing the pipe. So, of course, that borehole is lubricated with bentonite and other drilling fluids as we go through it, but we want to make sure that during installation, we're not going to pull that pipe apart. Mechanical weak links often help to show if it's going to break through that way. So pipe bursting, there's two types of pipe bursting. There's pneumatic, which uses an impact hammers that you see here, and then static uses a hydraulic power pack above ground and then quick lock rods as they go through it. So pneumatic pipe bursting only uses high density polyethylene because that impact hammer continuously presses itself up against the existing pipe with the wench, and then there's forces that happen as it moves through this. It's the only rehabilitation technique that can increase the ID of the existing pipe as it goes and moves through it. The city of Houston is one of the largest consumers of high density polyethylene on their wastewater side, and they have gotten their prices for pneumatic pipe bursting in many instances down below cured in place pipelining. So at the end of the day, you're going to put in an actual fitting and hard connection to pipe bursting, the main line to those lateral connections, and then you go from there. So static systems often have cutters, the abilities to break other types of pipe materials, as you see here, and we're looking at less social, environmental, and economic costs over traditional open cut. A lot of that has to do, obviously, with the less amount of excavation as we use this technique. So many municipalities understand that and look to trenchless technologies to do their rehabilitation work. So manholes actually are becoming more prominent, HDPE manholes in the past several years. And there's lots of different capabilities at the manufacturing plant to be able to provide HDPE stub outs for you to actually electrofuse or butt fuse down in the hole after you've installed this manhole. So we've just been asked conditions about how do you make manhole connections in seismic areas? And of course, the traditional way to do it is to use a grouted joint as you're putting that high density polyethylene pipe into the manhole. And that's that weak link then is what you put in the grouted joint itself. So if you had the ability to replace that manhole with a high density polyethylene manhole and then put in electrofusion or butt fusion connections, then your manhole is actually high density polyethylene too, which is a major benefit in seismically active areas. So slip lining is another technique, and instead of bursting, you're leaving the existing pipe in place. This is a very common rehabilitation method as to which you're simply pushing that existing pipeline through the replacement pipeline through that existing pipeline. You can grout the annular space or just the short-term connection as it goes through that, but it's very, very common to be able to use slip lining to put into existing pipelines. Long runs can be installed easily, further reduce that excavation as we're seeing it. So we're still taking advantage of the trenchless technologies. Richard, did you have something to add?
Yeah, and in that particular case, they did have to grout because they were burying it anyways, and the flange connection was at the other end. But usually that strap usually helps pull it through. But in this particular case, like you showed, we just pushed it in. and it went in. But making sure that your pathway is clear first and foremost, because if it's not, that was one of the questions that we said. So they cameraed that first to see that there was no obstruction or differential in the ID, especially at the bottom if they were pushing it in, because you wouldn't want that guy pushing it in that tractor to come through the windshield. So just be cautious of the safety factors around pushing. Pushing is okay, but just make sure that your bore path is clear. Thank you.
Yep. And then we bring to compressive fit lining, which actually uses a die or a series of rollers to temporarily reduce that OD of the pipe while we're pulling it into an existing pipe that often has a smaller ID than the typical OD as you're shown. So here, what you're seeing is the crew is spraying an oil on the pipe to be able to ease that transition. The forces that the machinery are providing through this are pretty significant. So we're looking at other ways to be able to temporarily help restrain those forces, such as a poured concrete dead man and other things, to resist that as it moves forward. These can be done for very long runs. And once the prep work is done, the actual process happens very, very quickly. So as I mentioned previously, HDPE will float in marine applications. And what we essentially do is we'll float out the long run of pipe beforehand, and then you'll put on an anchor to be able to make sure that you sink it to the bottom of whatever water body you've got through. And then that'll stay at the bottom of that water body as we go. So Richard, you got something else?
Yeah, when you look at this picture, what's really interesting is those collars are going to sink this line based on the buoyance calculation because it's full of air, but they go way, way down into the bay there that you can see, but it's all floating. So you can see your barge doesn't have to move. So it's very efficient in applying it. They've already measured out where the collars will go. And then once they fill that thing full of water, then it sinks down to the bottom. So if you ever wanted to maintenance that line for some reason or bring it to the surface, you just pump the water out and it'll bring all those collars and everything up. As long as it doesn't have erosion over top the collars, you may have to open them up a little bit. But it's a fantastic design. And this was a force main that was being put in, but it's a long line. But very, very cool technology.
Yeah, one of my favorite photographs in this whole show. Alan, quick question we got in. Back to grout. How do you grout the ends? Does they have to be done in lifts? You know, how far do you go in? You go in 20 feet. You know, what's the routine for grouting?
So grouting applications actually are a relatively complicated process when we start to talk about long runs and actually getting grout into the necessary places. So within a polyethylene pipe, since there's no corrosion within that polyethylene, you typically don't have to grout the annular space since it's not going to denigrate any of the pipe if it's not grouted. But what we look at is restraining the pipe ends as we go through. So you would typically push in a smaller pipeline or pipe that would be able to you could pump through, or a hose or something of that nature, as far as you determined you needed to grout the ends to be able to resist movement, and then you get that flowable mixture as you needed it designed and pumped into those annular spaces. Again, with HDPE pipe, since there's no corrosion within that existing pipeline that we have to be worried about affecting other pipe materials, then we're looking at just restraining the actual spaces. If you continued that installation and restrained outside of the pipeline, it would accomplish the same goal effectively as grouting itself. So we've got only a few minutes left. We've got one more installation method, which is called plowing. This happens when you got really good long runs that you don't have third-party utilities. They can actually just forcibly put this pipe in at burial depth as you really need it. It's amazing in long run applications when we're talking about needs for irrigation in farms or other things of that nature. With the remaining time that we do have, I would like to go through some a little bit on above grade, but we'll talk more about this next month. So please definitely join us then. And I'd like to talk about the resources that are available to you. Drew had earlier mentioned the engineer's package. It is voluminous. There's lots of information there, CAD drawings and details, specs in both Word and PDF. They cover a litany of different things that you could ever have to ask about high density polyethylene. So it is available on the website. Shoot Drew an email to be able to get to that. The website has a wealth of information for you in case studies as well. So see all the activities that the Alliance is doing in webinars, and hopefully when COVID's we'll certainly get lots of in-person meetings as well. And then Plastic Pipe Institute handbook on polyethylene pipe is included. It's a wealth of information for all things polyethylene, and a very useful design guide. It's included as a PDF that is searchable. So that is a functional element that I see fit every day to use. HDPE pipe calculator. This is something that PPI had created and has on their website to show you exact operating conditions of the pipe and whether or not it would meet the operating conditions as to which you would put it through. Borade, this is a planning document as well. So this is going to show you in a planning of a horizontal directional drill how much you have to transverse at depth. It'll push out a whole bunch of information for you as to whether or not that pipe would survive the installation and the demands that are put upon it during installation, and then whether or not that would survive in the long run from its operation standpoint. Here's some input parameters that are shown in PPI's PACE as well. So lots of good calculators online, to compare it to PVC and ductile iron pipe as well. The Alliance standard details does have connections, fire hydrants, manholes, installation methods, all sorts of information for you. And here's just some examples. These are, of course, available in PDF and AutoCAD formats for you to be able to incorporate as you need them. They're growing in leaps and bounds. We plan third quarter of this year to be able to put out the 2021 revision. If something is not in here that you would like to see, please don't hesitate to send us a question, a recommendation, and all sorts of other information for us to do. Again, I had mentioned manholes. There's lots and lots and lots of options with manholes itself to do polyethylene manholes and the various connections that you would put through it. Manholes oftentimes see some of the most corrosive environments of any collection system itself, and then this is set up for that. So Drew, if you'd like to rejoin us here, and we'll do some closeout for everybody.
Yeah, Alan, Richard, thank you guys very much. I promised everyone I'd get our emails on the screen one more time, so give me just a second to do that. There we go. So if you have questions we didn't get to today, you need a certificate to prove you attended today. If you have upcoming projects you'd like assistance with, or if you want that engineer's package, please shoot me an email, dmueller@pepipe.org. But all of us are available and eager to help you with any polyethylene questions you may have. So with that, Alan, Richard, thank you guys very much. This is a great program. And we will see everybody on March 10th when we talk, when we go into detail on above ground polyethylene installations.
Hey, Drew, does Darren have anything else to say here? Darren Zeppelin. He was gracious enough to be able to help us with the program.
Well, if he's out there, he's welcome to come on. Darren, are you out there? There he is. Darren, thanks a lot for making this possible today. Oh, you're muted.
Sorry, got to unmute myself. No, I think
There
it's
we go.
you've heard the best from two guys that have been in the trenches, so to speak, and literally and figuratively, and can't ask for anything more than that.
Great. Well, thank you, Darren. Thank everybody for attending today. We will see you next time. Take care.